Okay, so welcome back. This is the last video as a part of my prerequisite videos. So with today's session, we'll be completing the discussion of TCP IP, which will become a good background to get started into any of my courses, especially the network protocol testing and test automation course. Okay, so today we are going to look into the data link and the physical layer, the bottom two layers of the TCP IP. So essentially these two layers I'm going to put together receive the IP packet from layer 3. I think we spent quite some time on the layer 3, including subnetting. So the packet is received from the layer 3 and there is an encapsulation at the both ends. So you have a header here, you have a trailer here, and it is ready to travel physically on the line. And once it is received by the recipient, what it does actually is it will take away the headers and the trailer away and then take the packet to the layer 3 and above, right? So today we are going to talk about Ethernet as a specific example to describe the data link and physical layer. The reason is Ethernet layer is something which is a Ethernet protocol, which describes both data link and physical layer, is the most popular standard or protocol which is used, right? One reason for such popularity is that because it is simple and it's an open standard, right? So no networking discussion is complete without discussing about Ethernet. So what is an Ethernet? Ethernet originally was invented by Xerox in US, and thanks to them it was made open soon. Initially it was limited to LAN only earlier, so it's LAN technology only, for simple reason because the media, the physical media was just electrical, okay? But later optical fiber also became a part of the Ethernet standard, so it started traveling long distances, and therefore Ethernet became a WAN standard also, wide area network connecting two routers together. So under the Ethernet topic, we are going to talk about cabling, what sort of a cabling that is being used. We speak about the connectors. And since Ethernet discusses both layer 2 and layer 3, it includes both layer 2 and layer 3. For the sake of layer 2, what is the protocol it follows? So that's basically about the topic. This is a shorter video, but we are going to discuss all these topics one by one. So let's straight away head to the layer 2 part because we are coming from the application layer. We finished application transport and network. Now we are coming to the layer 2. And it's appropriate to talk about the protocol header and trailer. So this is an Ethernet header and trailer. So we have a preamble in the which is 7 bytes. What you see, the number is the number of bytes. You have a start frame delimiter of 1 byte. You have destination and source physical addresses. This is a MAC address, okay? Then you have a protocol type which describes about the layer 3 protocol, where is an IPv4 or an IPv6. And then you have the information or the user data that is coming from the layer 3, which has 46 and 1500 bytes as the minimum and maximum. And finally, you have a frame check sequence, which is of 4 bytes. So let's understand one by one in detail, okay? So one of the first job a layer 2 does, I think if you remember my TCP IP introduction, is framing. Because original application information can be pretty huge, so obviously it is divided into segments and then sent down. And in IP layer we saw what we call a fragmentation being done. So probably what is that you are seeing here in the user level is only a piece of data, right? So as it travels on the physical line to the recipient, one of the first thing the recipient would be interested in to understand when does a particular frame begins and when does it end, okay? So essentially you have a preamble which is nothing but a sequence of 101010 goes on, and it is 7 bytes, that is basically 56 bits, right? 7 bytes is 56 bits, 7 into 8. Now this indicates that the frame has begun. So carefully, for such combinations, 7 bytes of combination of zeros and ones will not happen anywhere else. So it's a very unique pattern that is there, alerting the user saying that, hey, wake up, there is a frame coming on your way, so get ready to process it. So after the 7 bytes, there is one more byte which is also a part of what we call as a synchronization to indicate the beginning of a frame, which is called start frame delimiter. Okay. Now, moment the start frame delimiter ends, the actual information for which the layer 2 is waiting or it is waiting to process will begin, right? So you have destination MAC address or destination physical address, whichever way you see, and a source MAC address. So what is destination MAC address? So at a layer 2, it will identify the next hop. So when I say hop, remember I was taking about postal system example when I was trying to tell you about networking, right? So you have an address written on it, which is maybe identifying the end destination. And to reach that destination, the letter need to be posted, right, in a post office. So what happens when you come out of your house to post any letter? What is the next hop? The post office. The destination is no doubt some other place, but your next hop is your post office. So likewise, an IP packet, when it is coming out of from a host machine, it has to reach a destination maybe several networks away, several routers away, right? So it has to be hopped around, right? So it goes to the first router, maybe the default gateway. From that default gateway router, it goes to another router, keeps on hopping till it reaches the destination. So always remember, in an Ethernet header, this destination identifies the next hop. This is not destination IP address. This is the destination MAC address which identifies the next hop only. Similarly, you have a source MAC address which identifies which is the machine which is sending it now. Maybe to begin with, it may be on PC to a default router. So the PC MAC address is the source MAC address. The MAC address of the router interface on which this packet is being received by the router. The MAC address of that interface is nothing but the destination, right? So you have the physical addressing being given. It actually is an identity identifying a particular segment where the packet is being going from one physical machine to another physical machine. Followed by, you have a 2 bytes of what you call the layer 3 type. So essentially we have IPv4 and IPv6. So we have discussed that in the network layer. So why in layer 2? Why this fellow has to do it? It's sort of an alert, okay? While the layer 2 is processing the Ethernet header, it's an indication to the host machine that the upcoming layer or the higher layer, layer 3, is either IPv4 or IPv6. To that extent, the host machine has an advanced information or an alert about the protocol to be followed to process the layer 3 later. So it's like an advanced notice. And then comes the user data. Now what is this 46 bytes to 1500 bytes? It's a collection of the original user information plus the application header, transport header and IP header all put together is a payload for the layer 2. It is actually the user data for the layer 2. Now keeping the frame synchronization in mind and ensure that it reliably works, out of careful design, there is a limitation has been set saying that it has to be a minimum 46 bytes and a maximum 1500 bytes. Now when you come to the maximum part, 1500 bytes, the IP layer takes care of it. For example, it knows that the next layer to which it has to pass the data is Ethernet, and it understands very well that the Ethernet can hold 1500 bytes maximum. We call it as an MTU, right? Maximum transmittable unit, okay? So if the original data is more than 1500 bytes, what it does, it fragments it. It cuts into 1 piece, 2 pieces, 3 pieces, depending upon the original size of the user datagram, and then sends it to the Ethernet. So as far as the maximum size is concerned, the upper layer, the IP layer, will take care of it. Now the question comes, if it is lesser than 46 bytes, what to do? Now you may be wondering, how can any user data be lesser than 46 bytes? Do we have such small messages? Probably yes, because many a times it can happen that the user data is not exactly a voice or a data or a video or whatever, but rather maybe a simple message, maybe a signaling message. Imagine we are using internet for voice communication, voice over internet protocol, VoIP, right? Voice over IP. There may be a signaling, probably asking him to disconnect a call, or maybe asking it to connect a call, or send a message saying that the end user has been identified and the ringing tone can be stopped. Often a smaller message. I'm just trying to set up, show you an example. So it's quite possible that the user data, even after adding all those headers put together, may be lesser than 46 bytes. So in that case, what Ethernet can do? Here the upper layers won't come to your rescue. The Ethernet layer has to what to do called padding. So if you see my description there, the sender adds padding to meet the minimum length requirement of 46 bytes. So you have to pad it up a bit so that it meets the requirement of 46 bytes and the frame is transmitted. Of course, the padding bytes have a specific place. Okay, padding bits, they have specific place. So the recipient would automatically understand that the whatever the packet it is receiving or the frame it is receiving, it does contain few padding bits. It takes them away and then collects the original user data, which is lesser than 46 bytes, and then passes it over to the upper layer, which is an IP layer, right? So that's how it goes. So the last portion is FCS, frame check sequence. So this is where it helps you to detect the errors. Now what happens whenever a packet comes or a particular data comes from the IP layer to the Ethernet, Ethernet actually follows a complex algorithm to calculate a 4-byte checksum. Okay, a 4-byte checksum following an algorithm, and attaches that to the frame itself in the end. So what constitutes this FCS is from the destination address onwards. So destination address, source address, type, and whatever the length of user data is there. That forms what you call a specific 4-byte combination. So as the bits are leaving the transmitter, so there is a calculation happens automatically. And once the data portion ends, okay, whether it's a data plus the padded bits, that portion ends, your FCS is ready. It is attached to the frame and then sent along with the frame. Now the receiver, for example, once it sees the preamble, it knows that the frame has begun. So the SFD off happens, it helps in synchronization. SFD also is there, so it's a part of the synchronization. The moment the useful information, the destination address begins, receiver also starts calculating FCS value on its own. That means there is an independent calculation at the receiver side too. So as the frame progresses and then it is being received, by the end of the user data, the receiver also has an FCS calculation calculated independently. Now that calculation which happened at the receiver is compared with the calculation done by the sender or the transmitter, right? If they are both exactly same, then the receiver believes that it got the ones and zeros, the bits, exactly the way sender has sent it. That means it didn't underwent any transmission error, some zeros being turning one or ones turning zeros. That means it's been an error-free transmission. So if the layer 2 is happy that the calculation done by the receiver FCS and the calculation done by the sender is tallying, the FCS is tallying, then it will pass the user data to upper layer for processing. For example, if it doesn't tally, that means some of the bits in the frame got inverted, there are transmission errors, then what happens? It drops the packet. So after the physical layer, the first layer that is that checks the data is Ethernet or the layer 2. At that very first opportunity, there is an error detection test that is happens. There is an error detection can happen, so that it doesn't want to send any frame which has gone through some transmission errors to the upper layers unnecessarily. So the packet gets dropped, the frame gets dropped right at the Ethernet layer. So all in all, if you remember my discussion in the TCP IP model, Ethernet fulfills all the functions of a layer 2. First of all, framing or synchronization. Second is physical addressing, identifying the next hop, source and destination at a layer 2 physical address. Third, of course, is error detection, and optionally it can do the padding also to ensure that the user data fits into these specifications. And that's what we expect from layer 2, right? It's quite simple, right? I know many of you already know about this, but just as a part of my preparation towards the later courses, I'm just sort of revisiting this. It is because of this simplicity, Ethernet is very popular everywhere. LAN, it rules it, okay? But even on the WAN connection, people go for Ethernet because it is simple to implement, simple to process, right? So let's look at the address portion a bit, because we'll spend some time on the MAC address, the destination source address. It is actually 48 bits in length. Of the 48 bits, the first 24 bits identifies the organization or the manufacturer of that product. It could be a PC, it could be a printer, it could be an interface card, it could be a smartphone, anything. Anything which need to be on the network has a physical address. And who assigns this address? The manufacturer himself. Unlike an IP address where you need to configure, whether you do it statically or dynamically, but IP address is something which the user has to configure, but not MAC address. MAC address is given by the manufacturer. So you buy a fresh or a new PC, it already has a MAC address in it. It's almost like a chassis number of a vehicle, right? You may have a registration number depending on the area where you register your vehicle, but the chassis number is given by the manufacturer himself. So the first 24 bits of the MAC address or an Ethernet address is actually identifies the manufacturer, like Cisco, maybe Juniper, or maybe Brocade, or maybe HP, or Alcatel-Lucent, any name, whoever is making, Samsung, Nokia, or Motorola, whatever is it. So it identifies the organization. And the balance 24 bits is a vendor assigned specific address of that specific piece of hardware. So for all, if there are a number of PCs or printers made by, say, a company called Hewlett-Packard, HP, their organization identity will remain same, but these keep changing depending upon the individual piece, right? So because it's a larger number, normally you represent in hexadecimal digits. We already discussed this in the number systems. When the number gets larger, you better use hexadecimal because it's easy to interpret, easy to understand. As an example, this is how a particular Ethernet address can look like. You have 34DE18, DE094, this is a sample, right? So that's about the Ethernet, okay? So now Ethernet address can be referred in many ways, and also within Ethernet you have what you call unicast, multicast, and broadcast. So I'm just going through some of them. For example, why it is called as a MAC address. MAC stands for Media Access Control, okay, because it defines the sub-layer of the IEEE Ethernet. So using a MAC, it actually identifies the next hop, right? You are actually accessing the next hop. So it is referred as a Media Access Control. We are accessing that. It can also be called as Ethernet address or a NIC address, Network Interface Card, or it can be called as a LAN address, Local Area Network Address. So there are other names, but they all mean same. Sometimes it is referred as a burn-in address because this is given by the vendor himself. He actually freezes the number, he burns into it. Okay? It's like something which you cannot change. Now address range can be anything, right, from all zeros to all ones, which in hexadecimal is all FFs. So if the MAC address is representing a single user, okay, then it is called as a unicast address. Very simple to understand. We discussed in our fundamentals, right? But if it is a broadcast address, that it is meant for everyone. Normally, what is a broadcast address? All ones. So if you see in hexadecimal, you have FF, 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 FF. So it's like, so you have like 12 hexadecimal digits. All Fs means this need to be broadcasted. So later when you actually start joining my courses, so I'll do several experiments where I'll prove this. If there is any broadcast situation that happens, in the Ethernet layer, the destination will be all ones. And finally, we have a multicast address. There are several protocols like routing protocols or even switching protocols like spanning tree protocol, which is to be implemented in several devices. Like spanning tree protocol is implemented in several devices. They all need to exchange some information. We call it as a bridge protocol data units, BPDUs. So identifying themselves and then identifying, which is the root ID, and if there is any topology change in the in the uh, in the network, so that need to be indicated, which is meant for a specific set of devices like switches, where in which the spanning tree is enabled. So when you have an information which is meant for specific set of recipients, you normally use a multicast address. For example, I'll be discussing STP during the course, but let me tell you right away, there is an address like, uh, 0180 C200 and 0000. That's the address, okay? It's a multicast address used by STP for native VLAN. I'm just slightly advanced topic. Some of you might be knowing what already. So when anyone uses that address, it is very clearly says that this has been dedicated for spanning tree protocol and it is meant for VLAN 1. Similarly, you have routing protocols like OSPF, EAGRP. At a layer 3, they have multicast addresses. Like for example, OSPF is 224005, right? Now there is an equivalent multicast address in the Ethernet as also, which is dedicated for OSPF. So likewise, there are some set of multicast addresses set aside for certain functions, for certain protocol group, for certain devices, enabling those features and protocols, right? So much like an IP address classification, you have a unicast, you have a broadcast, you have a multicast. So this is a bit of a additional information on the Ethernet address, very vital. So no packet is complete without you having the MAC addresses portion filled up, right? So it could be unicast or multicast or broadcast. It's just like if you don't know where the post office is, the letter can't go forward, right? You need to know where the post office is and then go and post the letter. So imagine you walking up to the post office, that portion, that information, where are you coming from, where it is going, is a vital first step or a step within the overall network communication. So you look at the Ethernet from a physical layer point of view. We have done with the layer 2, it's so simple and short. Now you look at the physical layer, so it supports various transmission speeds, okay? So you have 10 Mbps, you have 100 Mbps, you have 1 Gbps or 1000 Mbps. You have 1 Gbps with fiber and copper, so that's why you see that twice here, and you have 10 Gbps. I mean, there are standards which are much beyond this, so probably you can have a 40 gig and 100 gig connections also, especially if you are talking about a core layer of a network where the accumulated traffic is so high that they need a very high speed connections to handle the traffic, which is anyhow not within our topic today, but at an appropriate stage, if you happen to attend any of the CCNP courses with me or anywhere else, maybe 40 gig, 100 it will come into picture. Okay, so for the sake of our discussion currently, we'll normally stay up to 1 gig or 10 gig itself. So these are the speeds that it supports. These are the common names. So you have, if someone says Ethernet, strictly that means that it is a 10 Mbps link. If it is a fast Ethernet, it is 100 Mbps. Gigabit Ethernet tells it 1 gig connection, and then also if it is 10 gig Ethernet, obviously it is 10 Gbps. So these are the common names. People use it, but these are the names given by the IEEE. You have a 10 base T, you have a 100 base T, you have a 1000 base LX for fiber, 1000 base T for copper, and then of course finally 10 G base for this one. So these are the standard names, formal standard name. You can visit the website, take these details and understand more details about it. Except for the 1000 base LX, what we see in the list is mostly electrical in nature, and what actually the length of the cable, the distance it can travel without suffering any losses on the physical strength. That means 1 being seen as 1, 0 being seen as 0. That's what we want at the receiver, right? So the maximum length that they can support is 100 meters each. Of course, fiber is much better. So you know, fiber is a media where the light wave happens to be the signal goes, and the signal strength, or I would say the level changes in the light signal strength going up and down indicates the ones and zeros there, and they suffer minimal transmission losses compared to electrical. So as a result, it's a very protected media. It can travel longer distances without suffering much transmission error. So the fiber is always used for lengths which is longer, okay, so that it can travel longer distances without suffering any errors. Since Ethernet supports at various speeds, obviously switches also support various speeds, so you can have ports of different types. So you have a 10 Mbps as an access port, you can have 1 Gbps as an access port, you have 100 Mbps as an access port. But when it comes to linking the two switches, which is a trunk link, can be like 1 Gbps or 10 Gbps and also maybe fiber. The switches as a devices are more than happy to handle such things, because whenever traffic comes into a switch, it is actually buffered and queued, processed and reconstructed and sent forward. So when you are able to reconstruct a packet, obviously it can go at a higher speed, it can go at a lower speed, the media can be from, say, from electrical to optical and then optical back to electrical. So there is an isolation happening there, right? So when I discuss about switch in the courses, I'll talk about this particular switch internal operation much more. But obviously it supports what you call various speeds, and that is possible because Ethernet is supported at various speeds. Looking at the cable part, so most common cable that you see often in your home, office, everywhere is a UTP, unshielded twisted pair. Okay. So normally it's a pair of lines. For example, if a transmitter of a particular node is connected to a receiver of another node, it is often a pair of lines. So with a pair of lines, when you connect the cable to the ports of either end, the circuit gets closed and you have a current flowing into it. That's why whatever is being transmitted will go through the receiver, and then receiver picks it up and processes it. So it's always a pair of wires. And this is called a UTP, very popular, very standard cable for Ethernet. Coming to the connectors, so you have a cable with connectors. The connectors are RJ45 connectors, again pretty common these days. You walk up to any shop or any store, you can easily pick up these cables because they are completely like a consumer item these days, right? Even kids buy them, or people who are not necessarily in the networking area also use them. So it's a pretty common. So what you have on the cable is referred as a connectors, and what you have on the devices is called as a ports, right? So let's look at some of them physically. So what you are seeing here is a connector. I mean, pretty simple. What you have on this NIC card is the ports. This is a switch here, you have a ports. When it comes to the gigabit fiber, short form pluggable, this is an optical part. So especially this is used for an uplink. For example, if the switch has to accumulate and all the traffic that is coming from different devices connected to it, and then pass it to another switch or a router, it has to accumulate and send out probably over a long distance. So the data is of very high volume, and also the speed expected should be very high. And not only that, they have to travel longer distances. So sometimes the fiber could be a good choice there, right? Now looking at the pinouts now. So physical layer is all about that, right? So you see the cables, you see the connector, you see the pinouts. Now if it is a 10 base and 100 base, that is 10 Mbps and 100 Mbps Ethernet, they use 4 wires, okay? So you have a connector with 8 pins here, you have a connector with 8 pins here, of course there is a cable running between them. And you have two kinds of cable. For example, if I am connecting a PC to a switch, okay, then I need to understand one thing, saying that when it comes to the PC, out of the 8 pins, 1 and 2 constitute what you call transmit, and 3 and 6 constitute receive. But when I come to the switch, it is opposite. 1 and 2 constitute receive, and the 3 and 6 constitute the transmit. So obviously it's a common sense that the transmit pins here should be connected to the receive pins here. The transmit pin here in the recipient should connect it to the receive pins here. Because the numbers are opposite, a straight wire would do. You can see here 1 is connected to 1, 2 is connected to 2, 3 is connected to 3, and 6 is connected to 6. So the cabling has to be like straight cable. We call it as a straight through cable. So if you have a PC and a switch connected together, just make a one-on-one connection, 1 to 1, 2 to 2, 3 to 3, 6 to 6. So 4 wires, you connect them, your cabling is done, they happily work with each other. But in case you are doing opposite, for example, I have a switch connected to another switch. Now here the trouble actually is the pins are same, If 1 and 2 is receive here, 1 and 2 is receive also here. If 3 and 6 are transmit here, 3 and 6 transmit are here. Now I can't use straight cable, right? If I use straight cable, what happens? 1 gets connected to 1, 2 gets connected to 2, means transmit is connected to transmit, receive connected to receive. And that is not acceptable. So you use a cross wire. So 1 and 2 will go to 3 and 6. This 1 and 2 will go to 3 and 6. So depending upon what device you are connecting, you have to use straight or cross wire. So here a simple table. On one column you have a PC, router and a wireless access point. It's like a Wi-Fi router, whatever you may have. On other column you have hubs and switches. Now the transmit pins are 1 and 2 here, the transmit pins are 3 and 6 here. So like in the previous slide, if I am connecting a PC to a switch, obviously I am connecting 1, 2 of what you call transmit to 1, 2 which is receive here. And similarly, if I am connecting this transmit 3, 6 here and I am connecting to what you call 3, 6 here which is receive. So if I am connecting PC to hub or PC to switch, I use straight. If I am connecting router to hub or router to switch, I connect straight. If I am connecting a wireless access point to a switch or hub, I am using a straight. That means if you can draw this column, if you can remember this and draw this column, any cross column connection, that means a device in this column is connected to a device in another column, it is straight. But if I am connecting a PC to a router or a router to a wireless access point or PC to another PC or a router to another router, then it's a crossed wire. Similarly, if I am connecting one switch to another switch, it's a cross. Another switch to a, for example, hub or hub to a hub, it is to be a cross. So two same devices, if they are connected to each other directly, it is a cross. Any device within the column, it is a cross. Okay. So in my CCNA exam, I did that. Okay, a long time ago when I was writing that exam. So what I did actually is I just wrote this on my pad. You remember in CCNA they don't allow any writing instruments like pens and paper. Nothing they allow, right? But they give you a pad and probably a white marker pen so that you can do your calculation. So one of the first things I remembered, I wrote this table. So there were several questions. I don't remember how many, but there were a few questions related to this crosswire cable type and all that. So if you see the diagram below, so whenever I am connecting switch to switch, it is a crosswire, but whenever I am connecting a PC to a switch, it's a straight through. Simple to understand. I'm sure most of you must be already knowing about it, right? Now if it's a question of 1 gigabit, then I use 8 wires. Remember that was for 110 megabits, okay? But this is for 1 gigabit, I use 8 wires. So 1 and 2 and 3 and 6 will remain as they are, but they are joined by 4 and 5 and 7 and 8. So it requires 4 wire pairs, and now, for example, they use more advanced electronics that allow both ends to transmit and receive simultaneously on each wire pair. So that's what it is there. A straight through cable is simple, 1 on 1 to 1, 2 to 2, 3 to 3. So it's straight cable is no discussion. When it comes to cross wire, what happens actually? 1 and 2 will go to 3 and 6, 4 and 5 will go to 7 and 8. So you take one end of the cable. So you have 8 pins there. Another end of the cable, you have the 8 pins there. 1 and 2 will go to 3 and 6 on the other end. 4 and 5 will go to 7 and 8 other end. So similarly from this side also 1 and 2 will go for this. So it's a crossed wire for 8 wires. So that's about Ethernet layer 2 and layer 1. I thought this is a pretty simple video and fundamental to understand. My intention is not to tell you that you don't know about this, but it's always a way to get onto the same page so that later when we discuss the advanced topics in any of the courses I offer, we understand what we are talking about it, right? So this is the last video as a part of a prerequisite video. So I will see you on the training. So whatever training you are attending with me, I'll see you there, and then hope to find you there in my participants list and work with you, okay? And to make you whatever job ready, or make you more knowledgeable so that you can take up any task in the networking industry. Thank you for your patience. I know it's been a series of videos. You have been watching carefully and you are watching intently. So I thank you for that, and then see you soon. Thank you.